We have Sholto and Tristan. And I'll hand it over to Sholto to tell the details. But I originally actually was involved in this project right at the start. Due to time commitments, was unable to continue. But the key thing that I want to say here is that I think you started on this in like late 2018.
Yeah, we had a crash in 2018.
And yeah, like the key thing is that Sholto carried on working on this for like two and a half years.
Yeah, we got in the middle where we lost hope, and then we came back to us.
But like, I think that is honestly like the biggest takeaway here. Is he just persevered and persevered and persevered, and it was eventually able to like replicate some amazing results, which you're going to hear about tonight. And then also Tristan have also contributed significantly to this work. I don't know if you guys are going to present tonight, but just worth pointing out that these gents in the front here also contributed. With that being said, a big round of applause for Sholto as he presents his work tonight.
Haven't used a mic in a while. Does that sound right? Yeah, perfect. Well, thank you all for coming. I'm really excited to have Sydney Machine Learning back in person. I think it's a really great sign that we're coming back from COVID, and despite like the concerning cases down in Melbourne and stuff, let's hope that this can continue. So what we're going to be talking about today is basically our efforts mentored by a team at Google Brain to re-implement some of their research and now to begin building on it in new ways. And effectively what that centers around is robotic manipulation. And as part of this presentation, we're also going to cover what I think are some of the key milestones in robotic manipulation and like why it hasn't been solved to the extent that other AI subfields have been solved. So what you can see here on the top left is some of the more recent results, which are from pixel observations. So all it sees is the camera inputs, and it gets natural language as a goal. And so in this environment, it's actually able to complete a whole bunch of different tasks just from being typed out sentences of what you want it to do, off barely any data, like 2 hours of training data. And so actually at the moment, that's scaling a lot, and we've got a whole bunch more data in there, and so we're expecting to be far more capable over the next couple of weeks. But unfortunately, the results weren't quite here in time for today. And at the bottom is the results from about a month and a half ago, which is from states, and you can see that it's extremely accurate and precise and basically manipulating any part of the environment that it was given access to, and the transparent parts are the given desired goal states. So effectively it's able to reach any goal state in the environment with extremely high reliability, which is, to our knowledge, actually the best. I might hold this a little bit further away from it.
To our knowledge, the best open source implementation of robotic manipulation out there. And on the right, you can see elements which we'll explain later, and basically that's the plan space. So it organizes the behavior that it observes in this latent plan space of behaviors, and then sort of interpolates and generalizes through that to be able to manipulate the environment. So that's the agenda today. Why has AI solved things like Go, which all of us in this room probably find quite cognitively difficult, and yet it struggles with tasks which toddlers find trivial? Then the dominance of end-to-end supervised and self-supervised learning in everything but robotics, and our work and how robotic learning is evolving. So Moravec's paradox. Why is Go easier than building Lego? Does anyone have any thoughts?
Probably because there are rules.
Yeah.
Very well-defined rules, I should say.
Yeah.
And so it's operated, and you can predict. As a result, you can actually predict what's going to happen very accurately.
Yep, you can simulate out each individual step. So it's like a deterministic state transition that follows certain rules, and you know from the current state, like it's fully observable, right? Is the term. Like you know exactly what the state of the board is, and if you perform a certain move, what will happen as a result. Anyone else have any other thoughts?
No physics.
No physics? Physics is pretty damn tough. Yeah. So both of those actually play in. And just as a brief interjection, but the issue isn't hardware, right? Like teleoperated robots have been able to tidy things like that room 12 years ago. So that video is actually from 12 years ago. And even now, it's not like that we only have parallel jaw grippers. We have 5-fingered hand grippers, which are teleoperatable, and you're able to complete some pretty complex tasks with those. So effectively, the issue isn't hardware, even though hardware could do a lot to improve. The issue is very fundamentally on the problem side and on the software side. So part of the issue is that manipulation is much harder than our priors as humans suggest. We find manipulation really easy. evolved and we've grown up from birth able to do basic trivial manipulation tasks, and we find it extremely easy. When you look at something like Go, there's actually a lot of things which make it easier for computers. It's discrete time. It's got a discrete action space, so it's got this like finite set of action space, finite action space. You can effectively infinitely simulate it out very fast. There's no domain shift. The board and the game that you play is the game that you trained on. And there's deterministic state transitions, which means that you know that if you make a certain move, then you know if you can sufficiently model it, what the next state will be. And that is true theoretically of the real world and robotics, but it's just fundamentally not true in practicality. In the real world, it's continuous time. You have a continuous action space. Often you have very limited data. There's effectively never-ending domain shift because it's just almost impossible to actually cover the actual state space of all the different environments you might want to act in. There's effectively probabilistic state transitions, but it's so complex to actually model the world. And there's compounding error in that if you make the slightly wrong motions, then you'll deviate far away from your initial state state space, which is just really emphasized by the fact that there's limited data. So before we jump into learning for robotics, how has every other subfield evolved, and how is this going to tie into our discussion of how we think robotics should evolve? If you look at vision, that really went from quite a pipeline approach. So hue transforms and sift features and that kind of stuff, hand-designed features over images, highlighting particular things that people thought might be meaningful, like changes in contrast and particular edges and those kind of things. And then they'd combine those into maps, and then ultimately you try and classify off those. Nowadays, basically a convolutional neural network will learn all of that for you. It'll learn the feature extraction, it'll learn the circuits that combine them, and it will learn the ultimate classifier at the end. And that's actually quite a change from a very pipeline and segmented approach where you learn each individual, if you create something that can do each individual part, and then you replace it with something that just does everything end to end. So that's the software 1.0, software 2.0 distinction, which Karpathy often likes to highlight. And if you're interested in actually looking at the internals of how these algorithms learn, I'd highly recommend the Distill series on circuits. It's fantastic, and it really breaks down the fact that you actually can highlight individual neurons in the neural net as corresponding to different input features, and that there are actual genuine circuits that combine, say, different arcs into a circle at sequential layers of the neural net. It's similar with language. It used to be quite a complicated thing. So you had parts of speech tagging, tree parsing, once you've broken that down into parts of speech, named entity recognition, semantic roles, and co-reference resolution between those. And ultimately, all of that's just been replaced by basically transformers. You take input text, you produce output text. With things like GPT-3, you don't even need to specialize it on your, you don't even need to train it for your particular task. Often you can use the fact that you can transfer it, you can single shot adapt to any task just based on the context. So again, it's been simplified dramatically with an end-to-end approach. Automatic speech recognition is similar. You just take the audio signal, extract the Mel frequency coefficients, pump that into an acoustic model that determines the likely phonemes, pump that into a phonetic model, which pass those phonemes to determine what was a more likely sequence of phonemes, and then translates that into words, pass that into a language model, which is again like a spell checker effectively for the language, and finally you get the text. These days, you can do something like, there's recently an algorithm called WAV2VEC, which replaces the need for MFCC extraction at all into a basic ASR model, and it produces text out at the end. Self-driving cars would appear to totally buck this trend, and they are much more segmented into individual parts. So, and that's partly as a safety constraint, right? You want understandability, and you want to be able to say, well, okay, that module detects pedestrians, that module detects cars, that module breaks down lanes, etc. But actually, there's some recent trends in self-driving cars which would appear to disprove it, which would appear to indicate a trend towards more end-to-end approaches. So, for example, in recent interviews, Andrej Karpathy has said that with increasing data, instead of taking the outputs of 8 different camera streams and fusing them together with classic computer vision and SLAM mapping tools, what they just do is learn an end-to-end from the 8 camera streams into a map of the environment around them. With robotics, we're still very much at the stage where we have a separate perception planning control step. So typically you'll perceive grasp points in the environment using convolutional neural net. You'll plan a path through to get them. and then that you'll execute a form of control in order to reach and grasp what you desire to reach. That basically only scales to very simple tasks like pick and place and that kind of thing, except for in regards to control of the self and locomotion. So Boston Dynamics has obviously done amazing results, and they don't really use very much machine learning, or if any, in most of their results. But for most of robotic manipulation, where your primary interest is not in manipulating yourself, but in manipulating the environment, it's all about this perception, planning, control thing, where primarily the main area that AI is used is in the actual perceiving of like grasp points and that kind of thing. So it appears to work for grasping locomotion, but does it scale for more complex manipulation of the environment? And is there a way that you can take end-to-end perception and control, like perception and planning of the action space that you want to execute? So reinforcement learning is the typical end-to-end approach for robotics, but it's super, super sample inefficient. And reinforcement learning is really what proved that learning for robotics works. But because it's so sample inefficient, things like, for example, Berkeley's focus over the last year was offline RL, trying to make better use of prior data sets, because the primary inefficiency in reinforcement learning is that for most techniques, the assumption is you're learning online and you're learning it through constant interaction with the environment. I'm just going to go through highlight a couple of things that I think are particularly important in the journey of reinforcement learning from when it was really proved to be possible in robotics through the end-to-end training of diffusion motor policies, through to papers like continuous control of deep reinforcement learning, which developed the DDPG algorithm, which is actually often still used, DDPG or SAC. Hindsight experience replay really took the advances that were made here, which required a continuous function between, like a continuous loss function effectively for you to optimize over, and made it work, and made reinforcement learning work effectively on sparse environments. And that used DDPG, and more recent implementations use soft actor critic. Learning dexterity proved that compute equals data. If you can just arbitrarily scale compute, you can arbitrarily scale your data, and you can get really, really good results with an algorithm like PPO. But PPO, if you actually project forward here, is actually still used. So the innovations haven't been so much algorithmic in learning, because the actual algorithmic RL advances were all in 2018 and lower. It's been in better usage of data. So algorithms like Omega, I think, are really neat, because they take something like hindsight experience replay and they dramatically improve the amount of data that you're able, the quality of the data that you collect, and therefore learn way faster. Conservative Q learning uses data that you didn't collect. So instead of taking online learning, it allows you to use proper offline learning. And asymmetric self-play for robotic manipulation, effectively, it's again on that theme of choosing better data to collect. And I'll go through each of these in detail. But first, a refresher. So reinforcement learning is effectively us trying to learn a policy that maps from a state to an action. And in the most simple case, that's just a neural net, right? But we can decompose that into this constituent functions. The common pace-way paradigm, or the way we formalize reinforcement learning, is that you have your agent which performs an action which the environment perceives, and then you receive a reward and the next state, and your agent then takes in that next state, uses the policy to produce an action, and you get the next step in the environment. You can decompose this policy into the reward function, a discount factor, and the value function. You can also disregard that reward and value function, so effectively all the value that you will get from now, as the Q function, which, given your state and your action, it tells you how much reward there is to go in the environment. The policy is just a max function over the Q function. So you're just trying to maximize A over Q, choosing the best possible action given your Q function. So typically, the way that things like actor-critic algorithms are optimized is you learn the Q function through self-supervised learning, and then you use that to optimize the policy, right? So the Q function there is the critic telling the policy how good the actions that it proposes are. So guided policy search / end-to-end training of deep visual motor policies. Basically, the question they sought to answer was, how can we use a deep neural net to model a state to action mapping? And what they did was they trained initial neural net, so they stuck things like coat hangers in the robot's hand, and by doing that, they actually know where the location of the coat hanger, which let them train post CNN to estimate the current position of the coat hanger. They then could use standard control theory because they had a function which mapped from the pixels to the position of things like the coat hanger or the the hammer or the block and the wood that it was trying to be inserted into. And what that means is that they could use control theory to optimize this. Say, take the current state, which is like the XYZ position of the coat hanger as estimated by the post CNN, and then they knew where it was meant to be, and that's a smooth function, right, between where it is and where it's meant to be. And you can optimize over that function using control theory, which is using these local controllers to collect samples. So you learn the initial local controllers, you collect the samples, and you can train the policy to match the output of the theoretic controllers. So basically what that let them do is train a policy supervised by control theory. But can anyone think what are the limitations here? Like, what kind of environments couldn't you do that for? Keeping in mind that the key requirement here is that you have a post CNN that tells you exactly where the objects that you're manipulating are, and you know exactly where the object you're manipulating is meant to be. The key limitation is effectively that you need that smooth function between where you are and where you want to be, which is very similar to a dense reward function. In control theory, you just call it a cost function, which basically means that you can optimize down a smooth surface from where you are to where you want to be. So this is just like taking a random example from some prior work we did, where we're investigating the usage of tools. Basically, as you move that block closer to that, your loss function decreases, and you know that because you're able to measure the state of everything, which means that you can much more easily optimize the algorithm because you're using this dense cost function. But in reality, sparse reward functions or sparse cost functions perform much, much better because they tell you they let you avoid local minima. So basically a sparse function is totally flat until you get really, really, really close to your goal. And I'll highlight in the next slide why that matters. So let's say, for example, you knew nothing about your environment except that you wanted this green block to be in the green sphere, right? If you had a dense reward function, you could optimize that and you could use most reinforcement learning algorithms and they'd probably work. But optimizing that dense reward function is an absolute pain. So for example, there's this one paper where they learned to stack 2 Lego blocks. They spent months optimizing the reward function of exactly how high the Lego block had to be above the other Lego block before it was before the reward function transitioned to a downwards reward function, and exactly how centered it had to be before it transitioned, and that kind of stuff. Whether or not to discretize the reward function into approaching the block and that kind of thing. Hindsight experience replay took the idea of, well, why don't we just assume that you get 1 if you've succeeded at the task and 0 at all other times, so sparse reward function, and worked out how to actually extract enough signal from that you could learn. So typically, if you only got 1 when you succeeded, you would have to accidentally fail. You have to fail until you accidentally succeeded and then extrapolate from that. What hindsight experience replay did was they took anything that you did as a virtual goal. So even if you failed to achieve the goal that you were set, you get rewards for the goal that you actually did achieve. So if you were set this goal, but instead you knocked the puck there, they say, okay, well, in the case that you're given that goal, you got a 1 reward. And so you learned how to achieve that goal from which you can then extrapolate to achieving this goal. One of the key limitations here is that you actually have to achieve meaningfully interesting goals by accident to be able to extrapolate to future goals, right? So if, for example, your arm had to do something complex, like using the block, like the blue block to knock the green block, it's almost never going to accidentally move the green block. And considering that your virtual goals are all in the space of the green block, you're never really going to learn. Brief intermission. Learning dexterity is a massive, honestly, one of the most impressive usages of reinforcement learning I've ever seen. And basically it asks the question of, if data wasn't a problem, what kind of tasks can we learn? They use an absolutely absurd number of CPUs and GPUs, and they're able to learn manipulation of Rubik's Cube. I'm sure you've all seen the video if you're interested in robotics. If not, definitely search it up. Effectively, what they did was they used PPO, which is an algorithm that is still used today, and they optimized over an enormous amount of training data. It's well worth reading the paper. It's interesting. It's good to look into. But effectively, there's no core algorithmic achievements. It's just huge, huge amounts of data in a, like, effectively, it's a giant engineering challenge rather than a research challenge. But an incredible achievement in what they were able to achieve. So continuing that theme, how can we extract more signal from data? How can we just effectively, like, if we have access to more data, can we use that effectively? Yep. So learning dexterity. But what about if we want to use data that we didn't collect? So that's another key question in reinforcement learning that has been advanced about a year ago. Because all reinforcement learning used to operate like this. You have a robot which takes actions through a policy in the environment, so it receives experience, and then it loops through that many times. But to do that is really slow because you actually have to simulate out the robotics, right? What if you wanted to learn from past interaction? That seems like it would be possible because we do most of our machine learning in vision or language of other past data sets. But actually, all the assumptions break down. So, for example, if you're trying to estimate the Q function, which recall is the amount of value the amount of reward or value given for a particular action in a particular state, your learned Q function will approximate the actual Q function, but it will often have weird local minima in areas where you don't have data. And so what your robot is going to do is it's just going to exploit the local minima. So yes, this broadly makes sense and you're going to have to display the right kind of behavior there. But over here, you're going to do totally the wrong thing. And in robotics, that's just not okay. Because of the compounding error, you're going to enter an area where you don't know and you're just going to break down. So what CQL does is it minimizes all Q values. So effectively takes this red curve and pushes it down whilst maximizing the Q values under data. So maximizing the values of ones you actually know about, as well as just doing your standard Q learning update. And what that means is that you match the curve where you have data, and anywhere you don't have data, you implicitly assume the Q values or the value of actions are really low. So what this does is it means that anywhere you're uncertain, you constantly track back into areas of certainty. So that lets you use way more data than you would otherwise have used before. And this has been effectively Berkeley AI's main push over the last year, is how can we use offline data better? So we talked about how we can extract more signal. We talked about whether more data is really useful and whether we can use offline data. But if we are exploring, how can we explore the best data? You recall that with her, if you failed randomly until you accidentally succeed, then you aren't necessarily going to achieve anything meaningful. For example, her here totally breaks down in a basic maze case because it's constantly told to seek this goal here, right? And all of the goals that it accidentally achieves are here. In fact, if it extrapolated using a sort of basic heuristic of distance, it would probably keep running into this wall, which is basically what it does, right? You can see it sort of basically runs into that wall slightly more than it does here. That's because the only achieved goals that it gets, so the only thing it ever learns how to do is to reach here. And it just can't extrapolate from the fact that it needs to go all the way around because it doesn't ever accidentally do that. It just constantly tries to reach these goals that were set. What Omega does, and I think it's a really interesting approach because this is basically the only algorithm I've seen that can learn straight block stacking from reinforcement learning, apart from the one you'll see next, which required like 16,000 CPUs and 256 GPUs. So this one can learn block stacking on one machine overnight. And basically what Omega does is instead of taking the achieved goals that you did achieve and trying to backplot that through your reward function, it does that. And when you get given a goal, it replaces that goal that you got given with one of the goals at the frontier of your experience. So basically, if you pretend like this is midway through the Omega run, instead, if you were given this goal, instead of trying to achieve that goal, it would take the set of goals that you had already achieved, pick one at the frontier, and then try and reach that one, and then act randomly at the frontier. So it's constantly exploring at the frontier, which means that eventually it reaches there. Now, I think it's a really beautiful technique. Unfortunately, it really struggles in image-based domains because there's no like solid and known way to measure density in image-based domains. So you can measure that really easily in state space, but it's really hard to measure in image space, like the density of the state space. So, like for example, if you have like XY position, like this is effectively like if you just sample a whole bunch of points, like you know that this is like a high probability area, this is a low probability area that you visited. So you pick areas from low probability on the like distribution over the states that you visited. Whereas doing that in images just breaks down because like all pixels, it's like a continuous space. So this is another one on how can we explore better? And this is currently like the state of the art in terms of robotic manipulation, for sure. However, the compute requirements are absolutely insane. So they use like 16,000 CPUs and 256 GPUs. It's just fucked. But the method they use is really clever, and it's all about collecting better data. So what it is they have like two neural nets, one which is called Alice, which acts out randomly initially in the environment, and then one called Bob, which seeks to reach the same goals that Alice achieved. Alice is rewarded by Bob not being able to reach it, so it constantly tries to effectively escape Bob, and Bob is rewarded for reaching Alice. So Alice constantly tries to achieve more and more difficult tasks, whilst Bob constantly tries to reach those tasks which Alice achieved. So it means you actually explore out in the environment in like a sort of gradated curriculum, because as Alice improves, Bob chases it. And actually a paper on this came out, so this came out in late 2020, and a paper using effectively this exact method came out in 2017, and they had one really neat trick, which I thought like it's super simple, but a neat trick that allowed it to actually work on complex environments. Because initially people were only able to get this to work on like on ant maze kind of style things. And that neat trick was that they used behavioral cloning on Alice's trajectories. So instead of just having a reinforcement learning agent trying to reach Alice's goals and being rewarded for that, they actually just use straight supervised behavioral cloning on Alice's trajectories when Bob is failing to reach Alice. And that's all it takes for this to work on like crazy block stacking tasks if you have sufficient compute requirements. So reinforcement learning does work in some sense. I mean, it's super sample inefficient, it's not very robust. How to use offline data is an open question. Is there a role for supervised learning, as in vision, natural language processing, and automatic speech recognition? Or would, for example, priors help for RL fine-tuning? Like, is there a world where you learn a big policy using supervised learning and then you fine-tune that with RL? Probably not. Supervised learning drove many of those advances, but plain imitation learning, people have tried it a lot of times, and it's really quite time prohibitive and brittle. People have managed to make it work on a couple of block stacking tasks, but it's really, really tough. Besides, is supervised learning still like the core focus of what's driving advances in vision, NLP, and automatic speech recognition? I would actually argue that no. It's a slight twist. Self-supervised learning is what is enabling us to use far more data and therefore perform far better. So for example, Clip. You've all seen Dolly, I'm sure. Clip is key to be able to like rank the images that come out of Dolly. And how does Clip work? It doesn't work with a standard image classifier setting, right? So in a standard image classifier, you have all your images, they're associated with one of like 1,000 classes in the ImageNet case, for example. And then you try and choose probability over those classes. With Clip, what they do is they take a whole set of images and sentence labels on those images. And all they try and do is predict from which embedding of the image to which embedding of the text is the most likely paired. So basically what they do is they take like the paired image text embedding and they maximize the probability under the learnt representation that these two, like that this is one. So that image one corresponds to piece of text one. So for example, this picture of a dog corresponds to Pep like the Aussie pup and doesn't correspond to any of the other things. And what that lets you do is it lets you arbitrarily match what is the likelihood that this picture corresponds to this piece of text, which means you can then do classification far better than any classification model currently trained, or effectively better than in like 17 out of 26 image data sets, I think, was their comparison. But simply by listing those classes from the classic image, like say ImageNet, the ImageNet classes, and then using CLIP to determine which one of those it best matches and corresponds to. So that allows you to use extraordinary amounts of data because you can just take any piece, any image which has a text label. GPT, similar. It allows you to use any piece of text because your only objective is filling in the next word. You're not relying on labeled examples of like, question answer data set pairing, for example, of which there are smaller data sets. You're literally just trying to fill in the next word in arbitrarily picked sentences. So you can use any sentence for this. So the trend is really, you can use any picture as long as it has some textual description. There, you can use any sentence. In automatic speech recognition, actually, as of a couple of weeks ago, it's really similar. WAV2Vec doesn't use any paired examples of speech to text at all. All it does is it takes a whole bunch of speech audio, effectively k-means them, and tries to segment each of these k-means clusters into what corresponds to phonemes. Similarly, with text, completely unlabeled text, just it has to be from that language, obviously, they convert it to phonemes and then generate the phoneme sequence. And all they're doing is matching the likelihood of clusters with the likelihood of phonemes. So for example, the most likely cluster is going to correspond to the most likely phoneme in a particular language. And what this lets them do is do learning on any language, because labeled speech like audio transcriptions are actually a kind of annoying data set to get, of quite limited data, because they can train this across all languages at once. So basically, the idea is, can we avoid having to use explicitly labeled trajectories and just use generally collected trajectories and expand the amount of data that we use as much as possible? Because fundamentally, it is a data problem, right? You saw even in reinforcement learning, it wasn't core algorithmic advances that drove it. It was how can we find better data, extract more signal from data, use the data that we didn't collect, or explore better and collect better data. It fundamentally comes down to a data question. And self-supervised learning is one of the best ways of accessing any data accessing more forms of data. So has anyone done self-supervised learning for robotics? Bring Tristan up to talk about it. Thank you very much.
All right, so I guess this is where we come into the picture. So has anyone done self-supervised policy learning for robotics? And the answer to that is yes. There is this group from Google Brain who ended up coming up with this paper called Learning Latent Plans for Play. And so we came across this, I would say 2018 or something or other, it was a while ago. And we ambitiously tried to implement it for our final uni project. Failed catastrophically, but then weren't happy with that kind of failure and decided to give it another crack further down the line. And so the problem with reinforcement learning is you essentially have a lot of this uninformed exploration of the space, and you don't actually cover the state space very well. Whereas what they do is they essentially do play data. So they use a VR teleoperation, and they basically just essentially interact with the environment, collect this kind of arbitrary unstructured data. So rather than doing 1,000 examples of putting the block in the drawer, it's just you basically manipulate the block, put it in the drawer, maybe press the buttons, move the other sliding door and all that kind of stuff. And it's very unstructured and you don't actually have any kind of labels. And so, yeah, basically the only paper that actually showed better results than that was the asymmetric self-play that came later. But we thought this was a really good baseline for us to kind of go off. And I think we were quite keen on taking the self-supervised approach as opposed to RL, which we'd battled with over a couple of years and didn't have the best results. And so, yeah, we were really keen on essentially creating transferable baselines for any manipulation task. So what's really nice about this is you can essentially learn any task and do multitask robotics from this, rather than obviously doing one example of one task to death. You're basically doing a bunch of different tasks and then learning kind of shared information between them. And then we wanted to do some kind of transfer learning essentially, and you could easily kind of move that policy to different things because you've actually learned, I guess, transferable information.
And we wanted to take those advances from vision and language and apply it to robotic manipulation. And so basically, to give you kind of an overview of what this is like, this is like our simulator environment in PyBullet, essentially. We migrated it, though, to Unity engine a bit later. But basically, as Sholto told you, we have this like simple desk setup, and you're trying to essentially achieve those goals. So what would happen is we basically collect a continuous stream of 3 hours of data, no labels at all. It's just kind of like a big unsupervised data set. And then basically what we did was we'll essentially chunk it up, and the goal will just be, say, like t plus 30 time steps in the future. And that's highlighted by those, I guess, kind of like ghosted kind of animations there. And so it just basically tries to achieve what happened in the expert demonstrations sometime in the future. And so the way this worked is we do what's called like learning to plan, essentially learning this plan space. So by trying to reconstruct and repeat the actions, get to those goals, you can actually start to learn this kind of semantic plan space, almost like word to vec. You'd imagine you learn how to recreate the structure of a sentence, predict the next word. You can do kind of the same for like a sequence of robotic actions as opposed to a sentence, like it's another sequence learning problem. And you can basically learn these kind of semantic clusters, and we basically like hand labeled these ourselves. We just basically looked at a bunch of sparse examples, and then we were like, hey, these ones are interacting with the drawer, or these ones with the door and button, and we basically assign them a label. And that's kind of like a visualization of the plan space that this algorithm has learned. Okay, and yeah, so basically with play data, you have the big advantage of you're actually exploring a lot of the useful state space, as opposed to RL. RL is kind of like this purple bit here. It's just basically like random perturbations on like the current state you're in, and you're basically just like randomly moving around in the locality of that and trying to find new samples to kind of learn from. However, yeah, when you're doing expert demonstrations, it's a little bit better than that, but you're still kind of like quite constrained. But when you start going to play data, you're actually covering a hell of a lot more of the state space. So you can actually learn much better policies, be a lot more robust, and cover a lot more of like the kind of edge cases that RL would typically trip up on. And you can see here, obviously, when you're doing kind of random exploration RL, you're only really getting to like that amount of data. Oops, got it. Yeah, and essentially, when you're doing play data, it essentially like scales linearly with the hours of data that you're collecting, which is pretty incredible. And so it kind of makes sense to collect more and more play data. And so, yeah, if you remember Omega, obviously, this one, it becomes really hard to scale that to something like the robotics problem that we were doing. Works really well in 2D, essentially, where you're just doing this like ant maze kind of exploration. But when you're trying to do this like state space density stuff, and then you're bringing that up into like 7 degrees of freedom, like robot arm, that becomes really hard to estimate, essentially. Yeah, and so as a quick kind of refresher, I'm sure some of you are familiar with variational autoencoders, but that's pretty much like the backbone of how our whole system works and how the Google Brain guys did it, essentially. How it works, though, is it's a unsupervised learning model. You essentially take an input, and then you basically try and reconstruct it, and you essentially take the loss between what went in and what the model tried to recreate, and that kind of is what you back propagate through. But the innovation is what you do in the middle, essentially. You can think of it as you're trying to compress and have like an information bottleneck in the middle. And so you're trying to create like the most efficient representation. So obviously if you like over parameterize that kind of Z layer, it doesn't really need to do any compression, and it kind of hard codes, I guess, a lot of the training examples. However, when you force it into like a really reduced space, then it tends to encode everything in terms of like the basis vectors almost. And then you kind of learn to deconstruct from that sample down representation back into your full input space. So that's kind of like a typical autoencoder. Variational autoencoder is pretty much the same thing. Instead, you kind of learn probabilistic functions in the middle. So parameterized by like mu and sigma, which are just parameters of like a Gaussian distribution. And so you have like the Z, which is just like a somewhat like maybe like 256 multivariate normal distribution. And then you basically try and learn your decoder function, which maps it back to your output space, and then you just take the loss of like what you reconstructed with the initial, and that's kind of how you train it. But this is really good for like compressing data, People have used it for other stuff, like you can use it for doing like traditional compression. So say you have like audio or you have video and you want to learn like compression over that. People have created pretty awesome variational autoencoder, auto encoders for any kind of data like that. So we're basically running this on our robotic sequence data. And so how it kind of works is, we have a few different models here, I would say. We basically have our play data, which is just a big buffer of this like 3 hours of data, but we've done data augmentation on that. So essentially you basically run like a sliding window over it and you chunk up that 3 hours continuous amount of data into these kind of like frames where you have like 30 consecutive frames and you kind of slide that along. And basically what you do is you use an encoder, which is the front part of that variational autoencoder network. And this plan, what was it? The plan recognition, we call this like the encoder, essentially takes in the full sequence of actions. So say we have like 30 frames, I guess, of what would happen in that sequence. We basically chuck it into that and we try and reconstruct it essentially. And basically in the middle, it learns this kind of plan space, which was the kind of Z space that you saw before. So it's trying to learn to compress this very high dimensional space, which may be from states or from the actual raw images that you see here. And you're basically trying to condense it into this like 256 long vector or whatever it is. And this is like our plan space. And so it basically learns to encode all the useful information into that, kind of, I guess, avoid some of the noise. So that's how we create essentially our plan space, is just using like a typical variational autoencoder, trying to like, you basically decode that, the action decoder, it's like an LSTM essentially, like, so it goes through there, like VAE LSTM, goes out there, tries to replay the same sequence of actions, and then you essentially take the loss with that. And that's what's called your reconstruction loss, which is this guy over here. So that's how you train the latent space. And then we have a second encoder essentially, which instead of taking in the whole sequence, we basically like mask or just like cut out all the middle bit. And so we only give it the start frame of where it's currently at, and then the goal frame of where it kind of eventually gets to. And we basically wanted to learn like what plan should we sample from this space to basically do the, what you would typically do here for like inference, and find like the right plan to sample, and then kind of go chuck it to the decoder, and then the decoder will kind of replay that and hopefully be able to solve whatever the problem was. And so it's almost kind of like a indexing or some kind of like mapping into the space where you just take the start and end, and you're basically just trying to find what's the right plan to actually like achieve this goal. And then like the last part of what you usually have in a variational autoencoder is like the KL divergence term, and it basically does like regularization on your latent space, because if you don't do that, latent space, it just basically hard codes everything and it becomes very sparse, and you essentially don't map it to like the normal distribution. And then when you try and sample plans in here, there's a lot of like dead space, I guess, in the middle where you don't have any useful plans. And so if you regularize it, you get like a kind of nice Gaussian distribution, and you can basically sample plans, and it forces like plans that are actually similar in the space to kind of be clustered together. So I basically like walk through essentially what that's doing, but we basically just feed it the whole sequence, encode it, get the nice latent space, and then when we want to do inference, where we're like, hey, we're here right now, rather than hard coding and telling it what actions to do, all we do is like, we have a goal there, and it basically figures out what plan should I sample to get to that goal. And you don't need to really tell it anything in between. So that's that. But we want to firstly cover some of the challenges we ran into re-implementing this work, and talk about how it kind of drove our decisions going on from that. So one big thing that hampered us, I guess, was some of the data set bias. And I think this is like a general observation in machine learning, is it's like always a data problem. And typically if something's going wrong, it's probably your data and not your algorithm necessarily. But yeah, we basically had our simulator working, and we were teleoperating it pretty early on in the project. And we thought, hey, we just chuck some neural nets at it, it'll learn it, it'll be fine. That obviously didn't work. Basically, we were crippled for weeks because of how we collected the data, essentially. Because we weren't doing our like data collection while we were like teleoperating it, we weren't collecting it in like a background thread, and essentially like every time you would collect stuff, it would basically slow it down, and you got this like non-deterministic or like variable time stepping between frames, and that obviously becomes pretty impossible to learn. So we learned our lesson from that and kind of, you know, fix that so everything is like taken at a regular interval. Another thing was like rotation representations. We were using quaternion representations for rotations. Problem is, it's quaternions, I think, are quite discontinuous, and we found like hacks to get around that, but it wasn't ideal. And so instead we went to like the roll pitch yaw orientation, and we kind of essentially fixed the like domain of where the arm could actually rotate. It couldn't go past like, 360 degrees, and we kind of kept it fixed. And when you have those, domains that are essentially continuous, it becomes a lot easier for neural nets to learn. When you have discontinuities where it's going from like 360 back to 0 or something or other, that completely breaks your algorithm. And you see these like huge spikes where it just doesn't know what to do. So we found that to work pretty well. Those are some good fixes, and that saved us a lot of pain eventually. Another thing was like how you regularize. So I mentioned that beta term before, which regularizes to your Gaussian. And so there's some subtlety with that. And it's another bit of hyperparameter tuning, which we all love in machine learning. So yeah, basically based on our beta term, if you crank the beta term up too much, say like 5 times 10 to the negative 2, you end up over regularizing your space. And so the space kind of gets quite compressed. It's trying to pack too much information and fit it to like the normal distribution. And you basically kind of collapse the useful information in there. It's like over regularized. On the other side, if you go to under regularized, so say 1 times 10 to the negative 3, it actually doesn't have enough regularization, and it becomes quite sparse in terms of you have these like big open areas where there's actually like not encoded that much information. It doesn't really follow your normal anymore. And so you can't sample, I think, super effectively from that. However, if you get it right with a bit of tweaking, you can get to something like this, where you have like a nicely structured space and you can sample quite efficiently through that. Here you can see as well, we had our like action losses with our encoder planner, and then you also had your regularization losses here. And something that we learned pretty quickly was we always thought the reconstruction loss was like the ultimate metric for like how well your thing was doing. But regardless, we found that even with the over-regularized and under-regularized, they would all tend to like converge to pretty much the same reconstruction loss value. However, obviously the regularization would be quite different. So that became like not a very good metric for us to know like if a model was successful. And obviously when you're going off and running this thing on a TPU and you're kind of like looking at the loss curve and you're like, hey, this model looks good. And then it turns out you run it and the thing is just like complete garbage. So we had to obviously find more metrics and look into this regularization stuff.
Interesting, that's actually something we discussed both with the Google team and some people at Stanford who were asking questions about. And they've all found that reconstruction error is like a poor metric for end task performance if you're doing self-supervised learning over robotics.
Yeah.
For some reason.
Pretty interesting. Yeah, and like a good anecdote, well, something that happened essentially, we were training this model and we were at a stage where we're like, okay, we have everything right. We've kind of ironed out a lot of the bugs and we're kind of training it. I'd spent a lot of time optimizing this for like TPUs and putting it on Google Cloud so we can kind of throw max compute at it essentially. And so we'd train it and we'd basically be training it on like Colab. And as you know, with Colab, it like times out after 12 hours. So we'd run it for like a full Colab session. And we're like, great, after 12 hours on this like beefy machine, should probably be good. And so we were getting to like this kind of level up here where we're like, okay, it's probably fine. And then we would test the model and it'd still be complete garbage, to be honest. And we were thinking it was like plateauing at this point. But then, yeah, basically it turned out Sholto had the great brainwave of let's run it for a bit longer. And this brings up like the good Karpathy story of where he basically left this model running, I think, on one of his like cloud instances for like a long time, and it ended up becoming state of the art over like a period of a couple of months because he just forgot he was running it. So this pretty much happened with us. We just ran it for a bunch longer, like a couple of days as opposed to 12 hours. And magically, the loss kind of just dramatically improved after a certain point. I think once like both the encoder and kind of start kind of converging essentially, then the learning kind of speeds up. And so we realized we actually have to train our models a lot longer than we thought we would have to. But then our results got exponentially better from that. And we were able to do awesome stuff like this, where we can basically give it these goals and then we can try and perturb the space. We can throw all these blocks at it. And the thing amazingly recovers and knows how to kind of deal with those perturbations. And typically what we'd seen with our naive algorithms was like, once it would go off track a little bit, the errors compound and it comes into a space, as Sholto was mentioning, where it doesn't know what it's doing. But this was actually quite robust, I guess, to disturbances. Even if the block would fall off the table, it would be able to like go down there and pick it back up, even though it maybe only seen like a handful of demonstrations, which I thought was quite incredible.
Yeah, so like on this, typically like obviously with reinforcement learning, you're going to get full state coverage eventually. But our advisors said that they didn't believe that, like they showed it around the organization and no one believed that self-supervised learning or supervised learning technically could get results this robust. And it's all because of just like the insane amount of coverage that you get from play data and the fact that you're able to like extrapolate both, like that you map out this massive space in the area and you're able to extrapolate between points. So it's far, far more robust than other, like, than even most reinforcement learning methods, I think, to be honest, because you need to effectively have the block coming off the table and being successful at getting that reinforcement learning to learn this kind of behavior as well. It replans about every half second. So that's why it's able to like, adapt quite rapidly.
Yeah, and I think you mentioned all the Google guys really liked that tweet of where you put this video up. They thought it was really cool. Yeah. And so, yeah, basically I can probably pass this back on to Sholto, but the next kind of iteration of that was we went from just working from images and states and we started integrating language into how we were trying to learn that.
So self-supervised learning off the teleoperated trajectories is great, right? You only need to collect a couple hours of it and it's good, but you still need to actually collect teleoperated trajectories in those areas, like in those domains, in order to be able to learn them. And there was this paper they released quite soon after, which gave us an idea about how you could extend it in order to be able to use a far greater variety of data and thus use a far greater variety of operate in a far greater variety of environments. So grounding language in play. Effectively, question they asked here, what would be required to extend this to language goals? Now, if you recall here, you pump the goal into the plan proposal network, so the planner, and you also pump it into the action decoder. So effectively, all you're doing is pumping in a set of pixels, which is encoded by a CNN, into two different neural nets. What if you just replace the set of pixels with a sentence and pumped it through a neural net into the action decoder, right? Like super simple. And I guess why no one really tried this was it seemed like you'd need a lot of language examples in order to be able to do it. What they found was actually that you only need less than 1% of your data set to have language labeled examples, because you learn the majority of the tough part, which is control and interaction with the environment, off of the broader data set that you've collected. And all you need to do is effectively, it's like fine tuning in the end. Fine tuning the language to correspond to the image goals which were associated with that language. And so we also decided to re-implement that. And the current results are reasonable, but they're actually rapidly improving at the moment. So basically, we ported ourselves over to a new environment, which took a bit of time in Unity, because it's just got a little bit better. Like we found the physics were a little bit better, and we found it a bit easier to create environments and that kind of thing. And it's a little bit more like visually realistic. The VR experience is nicer and that kind of thing. So we collected this new data, got the language labeled algorithm working, and you can see it's able to even do some like reasonably complex tasks, like put the blue block, like in complex instructions, I suppose, put the blue block left of the red block. It's fantastic at doing the simple tasks like closing the drawer or opening the cupboard and understanding what that means. But it requires being quite close to the smaller and movable elements of the end to be able to do them, which implies that like the gripper cam is working really well, but the shoulder cam isn't. And I actually think I discovered the bug for why that is this morning. So it's really annoying that actually I wasn't able to solve that a little bit earlier, because I reckon the results for this would be way, way better. And if you look at like the loss curves tracking on weights and biases at the moment, they're already way better than the ones that this model did. So if you're interested, I'll show you some updates in about a week, because it should be some pretty cool results. So basically, now that we've got this working, it allows us to jump to the next stage of, can we extend this beyond scenes, which is being teleoperated in, by using language to bridge the gap between the robot-specific data set and more general videos? Now remember that you've got a plan space where you've learned representations of trajectories. So the green ones are like the door ones, the brown ones are like drawer ones. These are, so remember that like the door is near the cupboard, so the purple ones are like block plus cupboard. The blue ones are just general block ones. This is block plus shelf. So you're actually functionally organizing the different kinds of trajectories that you do in the environment. And we wondered, given that you have representations of trajectories, could you then encode videos of humans doing things and use contrastive learning to push the representations of trajectories that you know are similar together? So, for example, let's say you have a whole bunch of videos of humans closing doors and your own videos of robots closing doors. You want us to be able to understand that there are similarities between those two tasks. So in an environment which it is not acted in, if it's seen videos of humans closing doors and been able to map those via contrastive learning to its own behavior set of opening and closing drawers, then theoretically it should be able to open drawers in a new environment without having even seen it. And we've got current experiments going where we're trying to see if it can do that with first color transfer. So different buttons in the environment and changing the colors of those buttons, plus using contrastive learning against videos of robots pressing like the other color buttons and seeing whether it can learn to, say, interpret the instruction, press the purple button, even when it's never seen a purple button in its actual training data set before. And the reason that we thought this might be possible is effectively CLIP. So with CLIP, you're marrying up the image embeddings to the text embeddings in a sort of arbitrary set of data. We thought you might be able to replace, say, these ones with robot embeddings. They have the married textual descriptions and marry that up with videos of humans in diverse environments or videos of other robots in the same one. So effectively, taking a much larger data set of human video, your own data set of robot video, and using the sort of intersection in language as a bridge to be able to guide it, to how to interact in new environments. So can we extend this beyond scenes which has been teleoperated in by using language to bridge the gap between the robot-specific data set and more general human videos? So that's what we're working on at the moment. It's actually a pity because I thought we'd be much closer to this by this date, but we're delayed slightly by the issues with the language encoder. So this is coming up next. And how to do it? To use contrastive learning. Our original thinking was using pairwise embedding. So if anyone has done contrastive learning before, a really common way of doing that is pairwise embeddings. You take things that you know are the same class and things that you know are not the same class, or just randomly mine things that are not from that class. And so you push together with things that you know are the same class, and you push apart things that are from different classes. A new thinking is that clip-style contrastive learning might have a bit more stability. So by doing large batches of videos and text at the same time, you might be able to create just slightly more stability in that, because contrastive learning can be really unstable if you get the wrong pairings or you don't get good hard negative mining. Unfortunately, this is still a work in progress. So thank you all for coming. Really glad to have this hosted again. I'm really keen to have Sydney Machine Learning up and running again. Thank you, Paul, for taking the charge of that. That's awesome. So really great to be back here. Really keen to see what events Paul runs in the future. And just wondering if you guys have any questions about robot learning in general, some of the stuff that we've done. And just, I guess, something I wanted to highlight, which isn't on one of the slides, is that throughout this entire process, we had a lot of mentoring from people who are from the people who basically wrote the papers that we were interested in. And if that is something that you're interested in, like trying to build off people's papers or trying to take steps in research, we found that basically everyone is extraordinarily open to being reached out to through email. I literally don't think we've not been replied to. Because if you just send out an email with a clear description of why you're interested in the paper, you'd be amazed at how excited and grateful people are, even from crazy institutions, that you're interested in their paper and you want to build off it in interesting directions. And they would go out of their way to help you. So that's something I really recommend. If you take any takeaway out of this, it's that one, which is that if you're interested in doing AI research, it's take a look at what interests you and actually email the authors with ways that you think could be extended and see if they have time to chat about you with ideas of how that could work. Because that's number one, tip to actually, one, that helped us massively with actually getting all this stuff working, which is quite difficult. And two, it just generally might help you with the developing research taste. So, for example, one of the big ones, and one of the things that actually influenced some of the framing of the slides in this presentation was what is the question that people are trying to answer? And that's something that, like in this case, our question is, can we extend effectively the robot teleoperated data far beyond the data that it's actually been trained in, like to use the giant data set of human video that is out there to enable it to learn from more diverse environments in a similar way to it has been used in other self-supervised learning. But you'll see if I go back a little bit, that actually at the top of a lot of these slides is, like, for example, can we effectively learn from data we didn't collect? So reinforcement learning or just general like AI research is often motivated by quite high level questions that you need to like be really interested in the science of the question as opposed to the can we achieve this of making this like complex thing work, but rather like how can we find out if something we didn't previously knew would work will work. I think like the great example of that is like just even this one is like at the time it was such an open question of can we use a deep neural net to model state to action mapping. Like no one knew whether that would work at that point. And that was the question they set out to answer. So like the second takeaway, in addition to reach out to people and like just ask for advice or offer thoughts on their work, is always think about the question of like what didn't we know that we might be able to know as a result of doing this piece. So thank you all for coming.
Thanks, Walter. Thanks, Tristan and Tristan. Guys, do you have any questions? Because that was amazing. I don't know if you realize there was so much information in that, like 1 hour from like two years and a bit of work. Do you have any questions?
Oh, okay. Yeah, so I was wondering, so you can go from a particular instruction, like put the blue block to the left of something, to its translation in like whatever, the robotics simulation or whatever, right? So how can you predict how like well a particular action will be executed given a particular instruction?
So that's one of the I guess negatives of intent learning is you can't predict how well it's going to go. You can measure it by sampling out a whole bunch of different instructions and testing how it will perform. The only way that you can predict is through effectively empirical measurement, testing how different instructions go. Unfortunately, and this I think is a great problem, like think about in AI generally, is how can we predict how something will go, like how can we predict it in certain things more than I have in certain situations. That's something we still don't really have good grasp on, right? Like, for example, with a convolutional neural net, how can we predict what kind of classified sign when it hasn't ever seen an image like that? Can we, like, how can we predict how it's going to go under it? So that's something that a lot of control theoretic people, like base people, really find frustrating about AI, which is that you can't put bounds.
Just a question about the conservative Q-learning. So it sort of seems like almost the opposite of the usual optimistic bias, where you sort of want everything to have a high Q value if it's been unexplored, so that there's an incentive to go there. Would this push you in the opposite direction and cause you not to, in the learning procedure, cause you to not explore areas where you haven't explored?
Yep. And so that's why the emphasis is on big data sets for class interaction as opposed to online exploration. So with conservative Q learning, that's a fantastic question. You really pierce straight into the heart of what CQL is. Before this talk, I was like, no, Jen's going to ask me questions. You're not actually, typically you're not exploring online something like conservative Q learning, or only very minimally. Only to sort of add a little bit of stability around the areas that you're really going. You would want to try and combine that, let's say, with some form of like intrinsic motivation. Like, for example, you maybe want to set goals with something like Omega, or you want to use the asymmetric self-plate to create like a better curriculum. This Q-learning is, certain Q-learning is quite focused on creating safer bounds around that experience. Because sometimes it's sort of like, if you want to learn from a big data set of online interaction, otherwise. And again, like really open question, like how can you both, how can you both observe about areas you don't know, and yet also explore the right ones?
super open question. 3 hours in terms of data seems like a low number. Yeah. What do you think would be the main, like, first challenge you encounter to try to do that on the real arm, the real copper, real box? Yeah.
So one of the big reasons that we shifted from like Pilot to Unity is in this one we're actually like at each step we're stepping the environment, so we're totally controlling the physics from effectively the model stepping. Here the models are always running, the physics is always running in real time, and so that actually brought us up in a couple of instances, like the TCP connections, which were feeding us the image data, and like the lag between that and the action outputs. Like, stuffed us up a little bit because, and we had to end up having to talk to a bunch of the Unity devs that were working in robotics because the TCP library was but the interface with Unity was messed up. So worked through that with them. We got a dev branch up running, and that was one of the things we were talking about. So with a real robot, that problem would have been magnified, right? Like we were just going to have even more delays and between time and timing and stuff. But one of the things we hope to do is actually try and take that to a real robot really soon. So like this is all set up, so it's just like a ROS interface. So basically all we have to do to get that with a real robot is to set up like something which pumps out the image, get like broadcast image messages, and similarly set up something on the robot side which listens to the loading commands and connects. So it should be pretty simple to just sub in and out and see.
That would be really exciting to see.
Yeah, we're really keen to try that. We just wanted to get it like working slightly better. Like feel free to ask a question.
Shelton, can you go back to the architecture for the the model architecture that you used? Yeah, so it's like you're in training space, you have a whole bunch of plans, right? How do you move from plan to plan to achieve the overall objective? I know you've already described that.
No. So like the way that works is basically like if you imagine you start off here and your like goal is over here, what your planner network, this plan composal network will do is it will estimate one of the trajectories from that space, which will get you from here to here. And let's say you like try, you like don't quite successfully follow the plan, or the plan wasn't like quite correct, you then replan from here. So your actor operates at the full hertz of the environment, 9 frequency of the environment. The planner operates 1 second, every half second, or whatever. And sort of it's like a little bit of a look ahead to what kind of trajectory you want to do. And typically you won't follow the full trajectory because you want to like replan to correct. So a full trajectory might be this long. Like say we did like 30 to 50 frames. And you might say like follow 25 frames, you've gone slightly off track, and then from here you take another sample from the time process. You have a new current state and same goal state. And then, yeah, you like follow that new plan. So it's like go a little bit, and then you like check out where you are to go, and you replan potential route like this. You get started on course. Yeah. So you just constantly. So I actually always know like where you are right now, where you want to get to, so you can always kind of like resample.
So is one of the key things then like setting the look ahead size? Like
yeah, exactly. So look ahead size that like does impact performance. And you can actually see here is this dot that's moving around is the plan that it's sampling. When it's trying to achieve these goals, that dot is it. You can see when it's like pulling out the drawer, it jumps over the drawer space, and when it like gives just random block shit, purple block was covered, now it's going to draw a button, draw a button, draw a button. Now it's pulling out the block again, and then it goes to sort of standard block again. And yeah, like when it's putting something close to the drawer, it's the block. It's like the block closest to the drawer space. So basically, like this is constantly pulling that space.
Just to confirm it, the state space is purely visual.
For these ones, yeah.
And for yours?
This one has states.
This one?
This one has state. Yeah.
And then all is specified also visually, or you kind of have
Again, this one through language and through like purely visually. Here through states.
you have like long vector, and there is a space for each block, and you say that this block is going to be there.
Yeah, that's why it's like a lot more specific. We're actually like the loss curves now after the bug that I think is featuring better tracking quite closely with that. Like now, so theoretically, you should see the performance get pretty close. It's always going to be like slightly better. It's always going to be a little bit better from states. It just matters to see whether this is also, by the way, this is with so like 7 hours data. This is with 2 hours data. So like that is still in very much testing phase. It's just not quite that. But we scale up the data a lot, so it's now training 8 hours data, and it's that's it.
I've got one more question for you. If you your next update with running from YouTube videos or whatever you're using, if you get that working, can you make blog post or something or a video? And I'll post it out to everyone.
Yeah.
I'd love to be able to have that. That's so interesting.
Understand. We're pushing really, really hard. It's like kind of ambitious, but we'll see if we can a submission into conference on robotic learning in 20 days. So it's really, 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 really pushing the margin up. Like basically this training run now has to work. This takes like 2 to 3 days to train a proper one. And then we'll fine tune that with the video data set. Learning theoretically should work. We'll see.
All right, guys, let's get Schulte, Tristan, and Tristan a big round of applause. So that pretty much wraps it up for this evening. Feel free to stick around for a couple more minutes just to catch up with friends that you may not have seen in a while. And yeah, with that being said, feel free to reach out to Schulte or Tristan, or both Tristans. Probably some of the most smartest guys in this field in Sydney. I'm not just saying that lightly. Like there's very few people doing this sort of work. So thanks again, and cheers, guys. Thanks for coming out. Let's go. Thanks, Doug.
Yes, you guys. Hey, you guys. Yeah.
Mainly your bit. Well,